everyone. So we just left off last time talking about friction and giving the equations and some scenarios. I want to start doing some practice questions with these. So we'll start with this first one. So pause the video work itself and we'll go over in a second. All right, so in here we have a crate being acted on. They tell us that it's a wood crate on a wood floor. They give us the coefficients. They want the weight, all this other stuff. So first thing that I want to do, just want to focus on part A. I want to start with an FPD. Like I said, anytime we start dealing with friction or just multiple forces in general, we kind of want to make this FPD. You'll see why in one of the later questions. So if I go through it, we have Fg going down, we have Fn going up, we have the applied force being pushed to the right, even though it doesn't explicitly say that, I can assume. And then there's going to be friction going in the other direction. All right. So for finding the weight, that's pretty standard. It's Fg equals mg. Take my 20 kilograms times 10 meters per second squared, and I'm getting that Fg is 200 newtons. At this point, I probably would have added it to the FPD. So that's something I recommend for you when you make an FPD for yourself. Just start tacking on information there so that you're constantly updating it with the most current information. Now part B wants to know the force of the floor acting on the crate, which is basically this normal force. Now I know that since the block is, well, it says that it attempts to slide the wooden crate, meaning that it's going to end up sliding, or if it does end up sliding, it's going to go horizontally. Vertically, there's not going to be any motion. There's no acceleration. Therefore, I know that the net force in the y direction is going to be 0. So the sum of the forces in the y are 0. So I have Fn going up and Fg going down. So Fn minus Fg is going to equal to 0. That basically just means that Fn equals Fg. So Fn is also going to be equal to 200. Like I said, this is one of those things where you kind of want to get into the habit. You don't always have to write out, the sum of the force equals 0, blah, 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 in order to figure out something as simple as Fn equals Fg because there's only two forces. But if they want you to show work, this is how you set it up. If you go straight to Fn equals Fg, there's a good chance that you might end up losing points for not explicitly saying sum of the forces equals 0. The thing that led you to saying that Fn equals Fg. And you might end up making a mistake by accidentally just saying Fn equals Fg when, as we'll see later on, that's not always the case. All right, so I have my FBD. Like I said, I know that Fn is now 200. I know Fg is 200. Now they want to know the maximum force that could be applied before the crate moves. So since this is before the crate moves, that means that this crate is at rest right now. So we're going to be looking at the static coefficient. So once again, since it's at rest, I know that the sum of the forces in the x is also going to be equal to 0. So I can say FAP minus the frictional force is equal to 0. That means that the applied force is going to be equal to the maximum value that friction can be. Since I'm looking for the maximum force that could be applied, that's going to be equal to the maximum friction that could be applied. So I plug in less than or minus, since friction can be less than or equal to, mu s times Fn, plug my numbers in for the static coefficient, and I'm getting 84 newtons. So I can apply any force up until 84 newtons, and this box would remain at rest. And the friction will always end up balancing whatever I apply. Once I get past 84, even if it's 84.1, the object will slip and begin to move, and then we'll end up having the kinetic case instead. So part D says, well, what about if what's the net force when the crate has 100 newtons applied to it? So again, what we said before is that 84 is the maximum force that could be applied before the crate begins to move. So since 100 newtons is greater than 84, we know that this object is now in motion, meaning I need to figure out what the kinetic friction is by using the mu Fn equation once again, this time using the kinetic coefficient, which is in this case 60 newtons. So once again, I and we're going to do some of the forces in the x direction. This time it's not going to be equal to 0 because, again, it's moving and it's most likely accelerating since these two forces are not balanced. So we get 100 newtons minus 60. So we end up getting that the net force is 40. I can then set this equal into the equation F net equals ma, or sum of the forces in the x equals ma. 40 newtons in for Fx, 20 kilograms for the mass. So I end up getting the net force being 40 newtons and the acceleration being 2 meters per second squared. So this is just how you can see a friction question. I want to make a really quick comment and say that this is kind of on the, I wouldn't say the trickier end, but this is definitely a more involved question. The reason I want to point that out is I don't want you thinking that every question is going to be like this, but these are things that you will have to at some point keep an eye out for. You know, the idea of it saying, oh, there's 100 newtons applied, but them not explicitly saying that it's moving. You actually need to kind of get into the habit of saying, okay, well, what is the friction? What is the static friction? Is the static friction greater than the applied force? If it is, then the object's at rest, and we can just say that the only friction on it is static. If the static friction is the max static friction values is less than the applied force, then we know that the object isn't at rest and it's actually moving, and then we'll have to switch over the kinetic. So every now and then you might end up finding yourself switching back and forth between static and kinetic, because you'll end up having one moment where the object's at rest, and then they'll change something, and now it begins to move, and you have to kind of keep be on your toes and you know keep monitoring that situation. All right, so one thing that's always an interesting thought idea is, well, what would happen if there was no friction on the planet? We've talked about, well, you've probably learned about it in other science classes, that friction can be a big pain in the butt. It's one of the reasons why we don't have perpetual motion machines that can go on over and over forever and ever, because friction will always take a little bit of energy. It's why doing things in general basically isn't so easy, because there's always friction taking energy away. So some people might think, well, wouldn't it be great if there was no friction in the world? Well, the issue is that a lot of things run on friction. Us walking and sitting actually requires friction. Without friction, we'd be slipping and sliding all over the place. We wouldn't be able to hold on to anything since that requires friction. Nails and screws would just fly right out of their holes because friction wouldn't be there to keep them in place. Pretty much the entire world requires friction to run. So it's kind of an interesting thing that the thing that's kind of keeping us from progressing as a society as far as energy production cares, is the thing that's actually keeping the entire world running. All right, so here's the next question. Pause the video, works up, and we'll go over in a second. All right, so again, these questions might seem a little bit weird at first, but once you start getting into the habit of what they're mentioning, and you get a little bit more comfortable with the types of forces that we're dealing with, and you get more comfortable in drawing the FBD, it will start to make sense. So for example, here I have a steel container on a steel truck bed. Again, once they start making comments about materials, I kind of know that I'm going to be dealing with friction, but even if I didn't catch on to that, they want to know the acceleration that the truck can have before the container falls off. Well, if I really think about it, and I think about what force is actually causing the container that's on the back of some truck to accelerate forward with the truck. Because as we know, because of Newton's first law, if an object accelerates, there has to be an unbalanced force. So there's got to be a force that's pushing the crate along. And if I really think about it and I go through the entire list of all the forces that we have, the only one that comes to mind that makes sense is friction. Because I can imagine that if the truck bed was made of ice and very greasy, that the container would probably slide right off. So when they ask what's the max acceleration, that means one of the things I'm going to want to look for is friction. Again, draw an FBD. I know that there's a force of gravity going down. I know that there's a normal force coming up from the truck bed, and then I know that there's going to be friction pretty much pulling it forward. Um, and there's nothing else. Now, another way to think about why the friction is moving forward is, again, one of the things I had said before with friction is try to think to yourself, what would be the motion of the object if there was no friction? So, if there was no friction, this object would remain at rest. But since the truck bed is moving underneath it to the left, relative to the truck bed, there's that term from Unit 1. Because the block is moving relative and sliding relative to the truck bed, it's technically kind of moving to the right. It has to move to the right along the truck bed in order to remain physically in the same spot. It almost sounds counterintuitive, but if you really think about the difference between viewing what's going on from the ground level versus viewing it from inside the truck bed, it starts to make a little bit more sense. So the box relative to the truck bed wants to move to the right, so because the truck bed is moving underneath it, therefore friction has to be moving to the left. And besides that, there's no other forces. There's no tension force. There's no applied, no centripetal, no gravitational, or not anything like that. So these are the only forces. Since Fn and Fg are balancing each other out, that means the only force that could be part of the net force, which is causing the acceleration, is Ff. So if I'm looking for the maximum acceleration, that means I want to figure out what is the maximum frictional force I can get. And we know that the max occurs at mu Fn, where mu is the static coefficient. So I set the net force equal to the maximum frictional force, the max static force, Fn, because I didn't write this, but because some of the forces in the y equal to 0, I know that Fn has to equal Fg, and Fg equals mg. So that's where this setup is coming from. So I know that the net force is equal to this, which is equal to ma. Now, if I wanted to, I could start plugging in numbers now, but I actually want to leave it in variable terms, because one thing you should notice is on the left side of the equal sign there's an m, and on the right side there's an m. It cancels out. So it turns out it actually doesn't matter how massive this container is. This container could be 400 kilograms, 4,000 kilograms. Turns out that the max acceleration of the truck will actually remain the same. It'll be equal to the coefficient of static friction between the two surfaces times by the acceleration of gravity. So I plug my numbers in, and I end up getting that the maximum acceleration that I can get is 7.4 meters per second squared. So that's pretty much it. Just to put that a little bit into reference, that's basically increasing your speed by about 15 miles an hour every second. All right? About, yeah. All right, here's the next question. Pause video, work itself, and we'll go over in a second. All right, so we have this rubber crate. We're going to end up having to use the chart from the previous slide. I don't have it on here because I don't really have a whole lot of room. But the first part, it wants us to draw the FPD, so that's what we'll do. Again, we have the box, we have force of gravity going down, we have normal force going up, we have an applied force going to the right, and we have friction going to the left. Easy enough. They tell us that it's moving to the right at a constant velocity, or it's not moving to the right, it's just at a constant velocity. So I know that this entire system's in equilibrium. This is something that I'd want to box off and remind myself that I have. All right, so for part B, it wants us to find the magnitude of the frictional force on the object. So, well, I know that since the object's moving at constant velocity, we're using the kinetic information. So F of F equals mu Fn, where mu is the kinetic coefficient. So I plug my numbers in. 0.67 is the kinetic coefficient. I know that the normal force is going to be equal to 20. Again, I didn't really write it in here, but since Fg equals 20 newtons, I know that this is going to be equal to 20 newtons. So that means that the frictional force is going to be 13.4 newtons. One thing I want to point out is you'll notice that I am a little bit on the short of work type of side, and that's mainly because of just the nature of doing it on the PowerPoint like this. I don't really have a whole lot of room. So most of you will probably want to have to do a little bit more work than I'm doing now. Uh, Part C, they want us to figure out the applied force. Again, since I know it's in at constant velocity, that means it's in equilibrium. I know that the sum of the forces equals zero. So FAP minus the frictional force equals zero. So that means that they're equal to each other. Therefore, the applied force is also 13.4 newtons. All right, here's the next question. Pause the video, work on itself, and we'll go over in a second. All right, so one thing I want to do is I actually want to redraw this FBD. The way it's drawn is actually really confusing. So I want to draw it more standard. We have the weight going down, we have the normal force going up. You'll notice that I'm trying to use the same symbols that they used. We have friction going to the right, and we have this pushing force down and to the left. Like always, I don't want to keep that pushing force going on an angle, so I actually want to redraw this, but this time split that P at an angle as P cosine theta and P sine theta. They didn't tell me what theta is, but it doesn't really matter because I just need to get a relative value comparison. So from here, uh, since it's moving at constant speed, I know that the sum of the forces in the x direction equals zero, and the sum of the forces in the y direction equals zero. So from here, I can see that P cosine theta is equal to friction. But here's the thing, P cosine theta, I actually already know is a value that's less than P. Because cosine theta from trig has to be less than 1. As long as theta is, something that's not 0 or 90. So because I know that this theta is going to be some angle, I know that it has to be at least less than P. Similarly, if I do sum of the forces in the y direction, I get that N equals P sine theta uh, plus W. From here, I can actually see that since P sine theta is going to be, again, some number, I know that this means that N has to be greater than W because there's something a little bit more pushing down. And the normal force now has to balance both the weight pulling down, but also your additional force pushing down on it. So from here, I get that P has to be greater than F, and N has to be greater than W. So choice A is my answer. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so once again, first thing I want to do is draw an FPD. So draw my box, draw FG going down, draw FN going up, same old, same old. I have friction going to the left this time. And then I'm just going to add this in now. Normally you would have wanted to keep this force going up at an angle, but again, I'm trying to save a little bit of room here. So what I'm going to do is break this up into its horizontal component and a vertical component. So the horizontal would end up being F cosine phi, and the vertical component will be F sine phi. Like I said, it's going to be really helpful if you remember that the x component of any vector is going to be equal to the main vector, the hypotenuse vector, whatever you want to call it, times cosine of the angle relative to the horizontal. And then AY, the y component of some vector, is going to be equal to that vector times sine of the angle relative to the horizontal. So as long as the angle is taken from the horizontal side, like this, then these two equations pretty much hold true. So that's going to help out tremendously in speeding up the process. So I have my FBD. Now for part B, they want us to figure out the acceleration using the variables. Once again, if I'm looking at this, there's only one direction where it's going to end up accelerating. It's going to be horizontal. So I'm going to do some of the forces in the x direction. It's going to be F cosine phi minus the frictional force, and that's going to be equal to ma because it is going to end up accelerating. Just divide the m over and I get this. So it seemed like a very complex question, but it actually was pretty straightforward and pretty easy. All right, so here's the next question. What I want to point out really quickly before you start it, notice that question C is where I ask you to draw the FPD. Now, even though I'm asking you for part C to do it, you should still start off the FPD anyway. You'll see why I have it asked down at part C. But for now, try answering this. Start with the FBD. What I recommend is if you're having trouble starting this, at least watch the first part, pause it, and then see if you can continue on. All right, so pause the video, work on self, and I'll go over in a second. All right, like I said, first thing I want to do, like always, is draw that FBD. Even though I'm going to be doing a more official FBD later on, I still want to set it up. So here I go. I do my FG going down. Again, I can immediately find FG because I know that 6 times 10 is going to be 60. So I know FG is down. Now here's the thing. Because of the fact that the wall is now on this side, the normal force is not going to be going up. It's going to be going to the left. Because remember, normal force is always perpendicular to the surface. So the normal force goes to the left. Now, I also have this applied force going up at an angle like this. So that means since the force is going up and to the right, I should have a horizontal component, F cosine theta, which I can calculate right now as 50 newtons, like I said, just to simplify things. And it's going to have a vertical component, F sine theta, which is going to be 86.6 newtons. Now, there's one last force that I need to do, the frictional force. Unfortunately, it doesn't tell me anything about the motion of the object, and this is why we can't do the FBD yet. We don't know the value or the direction of friction. We don't know, and we also don't even know the type of friction. It doesn't tell me that it's remaining at rest. It doesn't tell me that it's moving. So it could be static. It could be kinetic. It could be moving up. It could be moving down. Don't know. So I'm going to have to leave it like this. For now, I'm going to say friction might be going up. We'll see. So part A says, what is the normal force? So, normal force, normally it's always equal to whatever is opposite it. So I could do sum of the forces. Since normal now acts in the x direction, it's going to be sum of the forces in the x. So it's going to be F cosine theta minus Fn equals 0. So Fn is going to be equal to this horizontal component, which I already found was 50 newtons. Now, part B is where I start actually thinking about what is the direction of the frictional force. Because like I said, I can't solve this without knowing that. So I originally said it's up, but let's see if that's even correct. Let me look at these forces again. So I have a vertical force of 86.6 newtons, and I have a gravitational force of 60 newtons going down. From the looks of it, just these two forces alone, I already can tell that I have a net force going upwards. This means that since the upward force is bigger than the gravitational force, that means that the object would go up without friction. So if this was a frictionless surface, I'd have a net acceleration going upwards because there would be a net force going upwards. Therefore, since the object would go up, friction is going to oppose that, theoretical motion and go down. So it turns out that the frictional force is actually going down. Now that I know that, I can actually adjust my FBD for part C and have friction going down. All right. Now the next question is another thing that I need to worry about is this object even at rest or is it in motion? Should I be using the static friction or the kinetic friction? Uh, so let's see. Well, in order to keep this block at rest, since we have an upwards force of 86.6 newtons and we have a downward force of 60 newtons, let's just see what it would be if the object was at rest. So I do my sum of the forces in the y, and I'm going to say that it's equal to 0. Because like I said, I want to see how much force is needed to keep this at rest. So I plug in my numbers, 86.6 going up, minus the 60 newtons going down, minus friction. That gets me that the frictional force needed to keep me at rest is 26.6 newtons. Okay, well, let's see what the maximum value that friction can be. So I know that f of f equals mu fn, or it's going to be less than or equal to mu fn. So I use the static coefficient they give me and the known normal force, 0.5 times 50, and I get 25. Because the maximum value that I can get from friction is 25 newtons, is less than the needed force to keep this at rest, this object is not going to be at rest. I can't be at rest. It won't be, there's not enough friction to keep this block at rest. Therefore, the object must be in motion. So I'm going to have to cross this out because this is not going to be needed anymore. The only coefficient that I care about now is the kinetic. All right. So you might even want to note that in your FBD that this is now a kinetic friction. All right, so for part E, we want to find the net force. Well, again, the only forces that are going to be unbalanced are in the vertical direction. So I do some of the forces in the y direction. We have the 86.6 newtons going up, minus the 60 newtons going down, minus the kinetic frictional force. So I plug my numbers in. I use the equation mu Fn here, this time using the kinetic coefficient of friction. And end up getting that the net force is 11.6 newtons up. All right, part F, now that I have the net force, everything's starting to fall into place now. To find the acceleration, I use the sum of the forces equal in the y direction equals ma. Plug my numbers in, end up getting 1.93 meters per second squared, also up. So this is a perfect example of pretty much the craziest that friction can get based on the type of information we can get right now. You're going to see a little bit later on how I can make it a little bit trickier, but the key thing here is that the FBD ends up being a crucial aspect, and you have to constantly take things one step at a time. Start calculating things, do what if scenarios, see if it works. If it doesn't, switch it to something else. So hopefully you can start getting some of the way that I'm approaching these problems and start applying it yourself to other problems. So I think this is going to be the last question. This one's another one that can get a little tricky. So pause video, work stuff, and we'll go over in a second. All right. So this question has two objects. Now, we haven't done multi-mass systems yet, so it it would make sense if you weren't too sure how to do this. Once we get to that point, this type of question should seem a lot easier. But this is actually going to be a really interesting question because it's going to take into account everything that we've learned so far, including Newton's third law. So what we're going to do for the first part is we're going to draw the FBDs. Now we have to be very careful with this. So we'll start with the top block since that's a little bit easier. We know that there's a weight going down and we know that there's a normal force going up. Because it's in contact with the block, only the block beneath it, I actually want to make it the distinction that this is the normal force from the block. And you'll see why I'm making this distinction in a second. Now, I know that there's going to be a frictional force caused by the rubbing between the two blocks, and I know that there's a tension force going to the left. Now, Why do I know that there's got to be a frictional force to the right, and why is it to the right? There's a few ways that you could go about it. First, it says that there's friction between all the surfaces, so these two materials are going to end up rubbing. Therefore, there's got to be friction. So whenever you have a rubbing of two surfaces, there's friction. Another thing to think of, when this block is pulled underneath, if I try to visualize the scenario at hand, like, and actually do this, because of this rope attached to the wall, this block cannot move forward. So it has to remain at rest. So when this gets pulled out, there's going to be a force pulling it to the right, causing there to be a tension going to the left. So I know that there has to be some force that's going to balance tension, otherwise there would be no tension. Another way to think about it, this is actually very similar to the truck bed question that we did before. When we slide the bottom block to the right, these two surfaces are rubbing. So relative to the scenario, to the floor, to this block is moving to the right. But with the respect to the perspective, I guess, from this top block, when you pull this block out, this block is basically moving in such a way that it looks like it's moving to the left. One way to think about that is because if you track like the ending point of this, the bottom piece, this bottom part will go from being right here to being over here. So it's going to move like this. Now, regardless of the scenario at hand, if this, the surfaces essentially are going to a point where they started here and then go here, that's the same as if I took this top block and just moved it over to the right instead. Sorry, not to the right, to the left. So either way, I can consider this as seeming like it's moving to the left. Therefore, there has to be a frictional force pulling it to the right. That one can get a little tricky at times, so sometimes it just helps to think about the whole idea about if there was no friction, what direction would be moving, all that good stuff. Now we have to get to the bottom block, and this is where it gets a little bit tricky, and I have to be very careful. So a few of these forces are pretty standard. I know that there's a weight going down, and I know that there's a normal force going up from the floor. Again, this bottom block is touching the floor, therefore there has to be a force pulling up. I know that there's an applied force going to the right. They tell me that. Now, the other thing is that I know I skipped one of these forces, and I'll get to that in a second. I know that there has to be a normal force from the top block pushing it down. Now, why do I know this? Few reasons. Again, there's multiple ways to think about it. Conceptually, if there is an object above you, you can feel the weight of that object pulling you down. When I say that there's a weight pulling down on this block, the weight I'm referring to is strictly itself. But because there's an object above it, I know that its weight is also pushing down. Therefore, I know that there's going to be a normal force from the block pulling down. I know this also because it's in contact with this is considered another surface, and normal force will always push perpendicular to that surface. Now, another way to think about this is essentially Newton's third law. In this first block, in this first FBD, I said that the bottom block exerts a normal force up on the top block. Therefore, according to Newton's third law, there has to be an equal and opposite force on the bottom block. Therefore, if the bottom block exerts a force up on the top exerts a force down on the bottom. These two forces are the same, hence why I gave them the same name, N block, in order to differentiate them from N floor. Now, a similar reasoning can be done for this friction force. Again, there's friction caused by the two blocks. So, using Newton's third law, I can do the same thing. There is friction between the bottom block causes friction on the top block to the right. Therefore, the top block causes friction on the bottom to the left. So This is just an application of Newton's third law. I had mentioned before that you'll see Newton's third law pop up in multi-mass systems. This is an example of a multi-mass system, and this is an example of how you use Newton's third law in these questions. So I just want to point that out there. Now there is one other thing, one other way that you can kind of realize that there's got to be a friction here. Again, because of the fact that it says there's friction between all surfaces, that means for every normal force I have to have a friction. I have a normal force from the block, therefore I have to have a friction from the block. But on the bottom block, there is a second normal force from the floor. Therefore, there is another friction force. So this is a very, like I said, this looks very complex, but it's a fairly standard setup. So now that you've seen it once, this question is going to get pop up a few different ways in slightly altered forms. It should become a lot easier from now on. You'll be able to kind of understand the trick behind it. So this is my FBD for the object. Okay, so now I can get to part B. Part B wants to know what is the normal force acting on the lower block from the ground. So we're looking for this Fn from the floor. All right. So if I look at my FBD, because of the whole sum of the forces in the y direction, the block isn't moving or accelerating vertically, I know that the normal force from the top has to be equal to these two forces, the normal force from the block plus the weight. So before I can figure out this, I need to figure out what the normal force from the block is. So using the top block, I'm going to do sum of the forces equals 0, the normal force from the block minus the weight. Therefore, the normal force from the block on the top is equal to W. Now that I know that, I can then go over to here and I could say that the normal force, that the sum of the forces in this bottom block is also equal to 0. So the normal force from the floor minus the normal force from the block minus the weight all equals 0. Plugging my numbers in, I get, moving things around, I get that the normal force from the block plus the weight has to equal the floor. Therefore, since I got W from the first one, I get W plus W. So I'm getting 2W as the normal force from the floor. All right. Okay, now for the last part, it wants us to figure out an equation for the largest force that F can exert before the lower block begins to slip. So again, this object is still in equilibrium. It's at rest. I'm going to use that to my advantage. So I do the same thing. Looking at this bottom block, I know that the frictional force, the force being applied to the right has to be balanced by the two frictions going to the left. Since the frictional force from the floor is based off of the normal force from the floor, and I already figured out what the normal force from the floor is, that means the only other force that I need to figure out is the frictional force from the block. That means I need to figure out what the normal force, I already know what the normal force from the block is too. So what I can do is combine all that together and figure out what my frictions are. So the frictional force from the block is going to be mu Fn, where Fn is the normal force from the block. Again, we're trying to maintain this consistency that we're using the friction of the block, the normal force from the block. From the previous parts, we know that the normal force from the block is just W. So I end up getting that this frictional force is mu times W. Going back down to the bottom block, I know that some of the forces have to equal 0 because again, it's remaining at rest. It's before it slips. So I have the frictional force to the right minus the two frictional forces is going to equal to 0. I already know what the frictional force from the block is. It's mu W. And I can figure out what the frictional force from the floor is. It's going to be mu Fn, where Fn this time is from the floor. So I plug in the 2W that I got from part B, I believe. And now I end up getting that F is equal to 3 mu W. Now, all this kind of makes sense if we really think about it. When we pull the object, it's rubbing against both the top block and the floor. So there should be two frictions. There's a friction from the top and a friction from the bottom. And because of the fact that there's going to be all this extra weight, there's the two weights acting down. There's also the force from the floor. That's a lot of forces going on that I had to take into account. So it makes sense that my total frictional force, or the total force that's required to balance out all the friction I'm feeling, should be equal to essentially three times the value that the top block is feeling by itself. All right, and that's pretty much it. So you can already see how adding in this aspect of friction really kind of jumps up and brings all these questions up one extra notch. But one thing to point out is that you should keep an eye out for how I'm incorporating Newton's laws into all this stuff. Now, there's a few more things I have to add on to the friction stuff, or not friction, sorry, to the forces conversation. We're going to talk about forces on inclined planes. We're going to talk about forces in multi-mass system and accelerated reference frames, all these other scenarios. And in each case, what you should keep an eye out for is how I'm incorporating Newton's laws and friction in there. I will point out though that these were the tougher type of friction questions, so these were kind of throwing you for a loop. First, I just want to point out it makes sense because, like I said, I'm kind of throwing out these tough friction questions right from the get-go. But don't expect every friction question to be like that. Um, that's just more of a, I wouldn't say it's a rare type of question, but more of an uncommon question. You should still be able to do it. And after a few practice questions with similar type scenarios, you'll start to get the hang of it. So, just like with everything, just keep practicing, just keep trying it out, and eventually it'll start to make sense. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.